All right, 8:30. How's the sound? Is it fine? Because lately someone was changing the settings. A ghost. So good morning, and I have a question about a situation we have already discussed before. In this case, again, we have a, well, not necessarily a cylinder, but a wheel, doesn't really matter, a ring, disc, mounted horizontally. And what we can do is we can attach a weight to it and see what's going to happen. Just let it spin. And by the way, what do you expect to happen if I remove these weights? By removing weights, I could reattach them to a different location, but it would take more time. Still, the wheel has much less inertia now, so we can observe that the angular acceleration is higher than before. Well, but that's not the case we have to discuss. We have to discuss a case if instead of attaching a weight, we just applying a force by our hand, and in the first situation the force equals 10 newtons. In the second situation the weight has the weight of 10 newtons. So question is, how do you assess the angular acceleration in both cases? This is a very common situation when you just have to solve two problems presented as one, but those are different problems. The problem number one, a force is applied to a disk. The problem number two, a weight is attached to a string acting on a disk. Two problems, you have to solve them. When you have to solve a problem, you don't do it in your head, because as you know, thinking is not required in physics. You do it on a paper with your hand. That's what's required. Drawing, writing. And the first case, of course, is absolutely straightforward. We've done it before. We just have to write the Newton's second law for rotational motion of these disks. And there's only, well, there are many forces, but only one torque. And that torque will be equal to magnitude of tension times radius, and that's supposed to be equal to rotational inertia times angular acceleration in a case number one. So the first case is solved by a straightforward application of the Newton's second law for rotational motion. A similar type of reasoning you need to repeat for the second situation. You need an expression for alpha 2. You look at that expression and it gives you a way to compare alpha 1 and alpha 2. And then you should choose your answer from this list. please again take a look, because I'm going to switch from this slide. Number one answer represents a situation when the higher acceleration is observed in the first experiment. Number two answer is for a case when higher acceleration is observed in the second experiment. If you think the angular acceleration will be the same, you can choose answer number three. If you think that with given information there is no way to answer this question specifically, you can answer 4. Don't choose answer number 5. There is never too much information. There is enough, and more than enough. So everybody who just entered the room has to answer 10 on the question 1. You're late. And question 2 already has a distribution. It was the same. So far is the most popular answer, which is unfortunately in physics, you know, democracy doesn't work in physics. Doesn't mean anything if the majority thinks the answer number 3 is correct. Doesn't have to be correct. That's not politics. That's what's good about physics. By the way, in 18, I think, 60-something, I don't remember, in Indiana, some senators introduced a bill. They didn't like that number pi had too many decimals. They wanted to round it up to 3. It's like rounding up G officially to 10. Make everybody make airplanes calculating G equals 10. Exactly same psychology in politics. That's why everybody has to take physics, to learn how to think scientifically. So in this situation, 3 is not correct answer. And we have a proof. All we have to do is calculate that acceleration. For the second object, the angular acceleration alpha 2 will be equal to the tension, but that will be a different tension. Number 2 times same radians divided by the same moment of inertia. It's the same disk. Well, technically, I don't know if the tension is different or same. That's another part of the reasoning. T1, T2. And the Newton's second law for rotational motion cannot answer the question about tension. However, lucky us, we have an additional object attached to the string, and we can use that object to relate other forces. So T1 equals 10 newtons. We know that. We can read. This weight has a force of gravity acting on it, which is also equal to 10 newtons. But this weight also will be traveling down faster and faster. So if you write the Newton's second law for this weight, we should write T2 minus W equals 8 points out, down, this. So T2 will be equal to 10 minus m times a. And it doesn't matter how heavy that attached weight is. It doesn't matter actually how fast or slow it's moving or speeding up. Does not matter. Because if we take a number 10 and we subtract anything from it, the result will be always less than 10. Any questions about this part of reasoning? Mathematics. 10 minus anything positive is less than 10. So alpha 1 will be equal to 10 times r over I. And alpha 2 will be equal to something less than 10. You can just pick a number, let's say 9 times r over I. So we need to compare two numbers. That means we have to make a selection from 3 possible choices. To do that, you have to compare two numbers, 10 and 9. So what do you say? Definitely not equal. Bless you. This is just, again, another illustration how the Newton's second law for rotational motion works alone, and when it works in a combination with the Newton's second law for additional object. Well, now we got to solve another problem. In this situation, we actually lifting weight. So we use the same system, but also there is a like a handle or a hand or a motor which makes this, I don't see anything here, which makes this wheel spin counterclockwise to you to make this weight move upward. So I don't have a motor, but I can do it with my hand. So that means I'm applying an extra torque. If nothing is touching the wheel, there is only one torque responsible for the angular acceleration due to tension. Plus, there might be some friction opposing this motion, two torques in general. In this situation, we have to add one more applied due to a motor or a hand or a crank. And of course, we know what to do. We have to just apply exactly the same strategy. So let's do it together. You do your part, I'm doing my part. So forces, mg, F tension. Done with the weight. Here, forces and torques acting on the disk. And again, there is force of gravity and kind of normal force, which don't really matter. Of course, we choose the axis of rotation at the location of the physical axis, so neither of these two forces have any torque relative to this axis. So where else we have? Well, tension doesn't go anywhere. There is a torque due to tension, but also there is a torque due to the engine, like applied torque. And because the wheel spins counterclockwise, the friction provides torque which is opposite to the motion, which means clockwise friction. That's it. That's the diagram analysis, force torque analysis. What's the next step? Equations. One equation for the weight, a standard Newton's second law which says tension minus gravity is equal to m times acceleration, which, oh, sorry. Now it points up because the object is moving up and speeding up. So acceleration now is positive. That makes a difference. But forces up and down. Okay. Now the Newton's second law for rotation for the disk. Counterclockwise is positive. So applied torque is positive. All right. Friction provides a negative torque counterclockwise. Tension provides a negative torque. Done with torques plus 2 zeros because of gravity and normal. And that has to be equal to the moment of inertia times angular acceleration will be also positive. Angular velocity is positive and it's speeding up. And as we know, because the string is ideal, well, first of all, because the string has no mass, the tension acting on the weight and the tension acting on the wheel or disk have the same magnitudes, as we know. Plus, because the string doesn't stretch, which means if the weight travels up a certain distance, like 1 centimeter up, a point, we can use a marker here and look at the motion of this dot. This dot travels exactly the same distance, and that means the linear variables and angular variables related to each other by standard set of equations, like theta equals S over R, or omega equals V over R, or angular acceleration equals tangential acceleration over R, and tangential acceleration of any dot on the disk will be equal to linear acceleration of that weight, because the string doesn't stretch. So we got so many different expressions, and now we know, well, we can add some extra expressions. For example, where else do we know? I, because it is a disk, the moment of inertia equals 1/2 mass of the disk times the radius of the disk squared. Where else do we know? The magnitude of the frictional torque should be equal to 0.1 of the applied torque. What are we looking for? Now we have to ask this question. That's actually what we're looking for, the applied torque. But we know the acceleration of the weight, 0.1 meters per second squared. So this variable A is given to us. And of course the radius, the masses. So now the strategy is absolutely clear. We know acceleration, we can calculate angular acceleration. We can calculate moment of inertia, so we can calculate this product. And if we know acceleration, the mass, we can calculate force of tension. If we know tension, we can calculate this torque, and then we plug everything in and calculate the torque we are looking for. That's math. What we should write here, physics was done. And this is a mathematical exercise I would recommend to do at home. All right, another example. Now it's a sphere with a given mass and diameter, and it spins. So we have like a needle which passes the center of mass of this sphere, and the sphere spins about it. And what I'm using right now to paint that picture is my imagination, my ability to imagine things, to make a transition from textual description to visualization. If I wouldn't be able to do that, I wouldn't be able to solve this problem. Of course, the next step would be drawing a picture which represents what I see in my mind. So, okay, we apply normal force, and when we apply normal force, that normal force generates force of friction. Well, in a way, we can use this as a model. It was spinning. We apply normal force creates friction, friction slows it down. That's it. And we just have to follow this strategy. Well, does it look like a sphere? More or less. More importantly, to describe the fact it's a sphere, we can immediately write the coefficient 2/5 for the moment of inertia of a sphere. And if we want to, we can calculate it immediately because we know the mass, 10 kilograms, the distance, 1/2 meter. Okay, and the initial angular velocity is equal to 60 radians per second. Why is this important? Why is it important that axis goes through the center? The answer is because of the way we are calculating moment of inertia. Because if you remember, we said it a couple of times, if we move the mass away from the axis, it changes the inertia. It makes it larger. If we move the mass closer to inertia, it also changes. And what could we do? Instead of pinching the sphere through the middle point, we could pinch it, well, through a side point. And that would change mass distribution about that axis, and that would change the inertia. How? We don't care because we don't have to know. As long as the axis goes through center of mass, the inertia always 2/5 mr squared for the sphere, or 1/2 mr squared for the disk, etc. So the force we are, well, let's say it spins, I don't know. Do we know how does it spin? No, so we can choose. Let's say it spins like shown, like this. And we are applying a force. And that force generates friction. Now, in this picture, we wouldn't see friction because friction would point at us, trying to slow down. We have a symbol for that direction. At us means out of the screen. So this is how force of friction would point. But we can choose the point of view. Let's say we look at straight down. In that case, this is the same sphere, but we wouldn't see the axis. The axis would become just a dot. But and the sphere would be spinning, let's say, counterclockwise. And the normal force, well, applied force would be seen directed to the left. And now we could see the frictional force. This is an important practice, switching from one point of view to another point of view, back and forth. Again, using our ability to visualize things. Now, of course, the sphere acts on the hand. It could have been a hand, yeah. but the sphere acts on a hand with the same force but opposite direction. And as we know, frictional force and normal force are related. And do we know a coefficient? Yes, we know a coefficient. So 0.8 times force we are trying to apply. What else do we know? We know that the angular velocity changes from 60 to 2 radians per second in 10 seconds. Well, okay, so we can calculate the angular acceleration. 2 minus 60 over 10, 5.8, negative 5.8 radians per second squared. Why is it negative? Well, because if angular velocity points counterclockwise, angular acceleration should point opposite to that because it's slowing down. So clockwise and clockwise means negative. But if we want to calculate the force, we can use just magnitude. So magnitude of torque of friction should be equal to I times magnitude of alpha. On the other hand, this torque should be equal to force of friction times the radius. On the other hand, this should be equal to 0.8 times normal force times the radius. On the other hand, that should be equal to 2 over 5 times 10 times 1/2 squared times 5.8. And if you write it like this, sorry. I also want to replace the radius with a given number because we know it, which is 1/2 meter. Yeah. If we write this whole expression, there is only one unknown left. So easy to find that unknown now. Just take a calculator and calculate. Any questions? Yes. It's 50 centimeters. Thank you. Thank you. I could have said I did it on purpose to check your attention, and I'm not going to lie, I just missed it. So the radius should be 1 over 2. Easy fix, easy fix. So 1 over 4 times 2 times 2 times 2. Where else? I think that's it. Okay, fixed. Why? The more important question, why did I make this mistake? Because I didn't list it as a given variable. That's what I should have written. If I did it, I would immediately make a conclusion. But I didn't. Because by some reason I wanted to think, and that was my mistake. Well, moving on. Of course, a spinning object stores kinetic energy. For example, to make it to spin, I have to apply a force and do some work. There is a... All right, let's see what I have here. I don't need this for now. How would I calculate the work? Oops. Well, I could just calculate the work done by my hand on a rope or the rope on that cylinder with a disk. And we will do that on the next slide. What we do see here is how to calculate the total kinetic energy. We just have to add kinetic energy of each individual part of that solid object. For a single point, for a single small dot, kinetic energy equals 1/2 mass times speed squared. And as we know, linear speed, angular speed related. What is so bad about the linear speed? It's different for different locations, but angular speed is the same. So if we make a transition from linear variables to angular variables, we get a very simple, convenient equation for calculating kinetic energy of a spinning solid object, very similar to mv squared, but instead of mass, we use other inertia, rotational inertia, and instead of speed, we use other velocity, angular velocity. And if we want to calculate work, we could do, well, we could start from an expression for work done by constant force. You know. We can measure the distance traveled by my hand or by any point in the rope. Force times distance is work. However, we also can make a transition from linear variables to angular simply by multiplying and dividing by the radius. First variable is torque we're applying. Second variable is what you have to tell me. That's the question number 3. Theta. What does it represent in this equation? Theta is a very common letter. It represents many, many different angles. When we write a letter, we have to know the exact meaning of what it represents. How much work did I do? Much more than yesterday. If I want to stop it, I also have to do some work because I'm changing kinetic energy. Well, there's no tricks here. Distance divided by radius is a definition of radians. It's an angular displacement. So this theta represents angular displacement. This expression tells us the magnitude of the work done, but the actual value of work can be positive, 0, or negative, as we know. It depends on the direction, on the angle between force or displacement, and in this situation, it depends on the angle between torque and angular displacement. And how does torque point? Counterclockwise or clockwise? How does angular displacement point? Counterclockwise or clockwise? That's it. So they only parallel or opposite to each other. Nothing else might happen. If they parallel both clockwise or both counterclockwise, there is no angle between those two. 0, cosine of 0 is 1. Work is positive. If the opposite, angular displacement, let's say, clockwise, and the torque is counterclockwise, the opposite, cosine of 180 is negative 1, the work is negative. Well, and of course, when work is done, that changes kinetic energy. We can use the same work kinetic energy theorem. Kinetic final minus kinetic initial is equal to work done by all torques. Some might do positive work, some might do negative work, some might do no work at all. If we add them up, net work tells us what's happening to kinetic energy. Net work is 0, nothing happening to kinetic energy. Angular velocity remains constant. Net work is positive, so energy increases. network is negative, energy decreases. We kind of slow it down. What is the minimum amount of work needs to be done to speed up a disk from rest to a given angular speed? Work kinetic energy theorem immediately gives the answer. So first, of course, we have to write kinetic final minus kinetic initial equals that amount of work we are looking for. If it starts from rest, initial kinetic energy is 0. Final kinetic energy is the number we are looking for because it will give away the answer about the work which should be done. So all we have to do now is just apply an expression for rotational kinetic energy, which is 1/2 times rotational inertia times angular velocity squared, which is 1/2 times rotational inertia over disk, also equals 1/2 times mass times radius squared. That's a radius. And the only kind of tricky part is converting revolutions into radian. Well, not forgetting to convert revolutions into radians per second. 100 revolutions, and each revolution is equal to 2 pi radians squared. And that will be joules because it's work calculated using international system of units for everything. Radians. At this point, we just have to take a calculator and finish punching the buttons. Well, now, of course, as scientists, we're always looking for similarities, connections. For example, when we talked about linear motion, we used the law of conservation of linear momentum, which we derived from Newton's second law under condition net force acting on a system equals 0. So we can ask the same question. If net torque acting on a system equals 0, anything interesting might happen? Yes? We can use the same type of reasoning to rewrite the Newton's second law for rotation. So that's the net torque, but instead of using angular acceleration, we can switch to velocities over time, and that gives a new kind of variable which is equal to a product of rotational inertia of an object and its angular velocity. V times m, m times v, mass times velocity, we used to call it linear momentum. Now we get a new quantity, so we have to name it. And of course we call it angular momentum. We have to label, give it a letter, a standard variable which represents angular momentum is a capital L. And of course, now we can make a next step in our reasoning. Every time when net torque acting on a system is 0, angular momentum of a system should remain constant. What's happening inside doesn't matter. Question. What do you expect will happen when this lady pulls her hands toward her body? Not my day today. I almost tripped over today on my way to work. but that doesn't scare me. I'm going to try this experiment. All I have to do is just spin myself. And move my hands with weights, because that makes change in inertia larger. So this experiment should answer you the question. When my hands are far apart, my inertia is large. And when I move my hands, or she moves her hands closer, that decreases inertia. But because the angular momentum should remain the same, the product should remain the same, decreasing inertia means increasing angular velocity, so it spins faster. Probably you saw it if you ever watched figure skating. There are many, many situations similar to this. For example, well, I just did this, but instead of a chair, I used a turntable. Okay, so let's see if I can do this with this one. The top experiment, well, instead of a ring, I have just a weight. So it spins. And now it clearly slows down. What happened? Well, of course, by adding this weight to the system, I'm increasing I inertia. But because net torque equals 0 about this axis, the total angular momentum of the system should remain the same. So if I goes up, omega goes down. And people use this physics to make toys. Well, that's actually a game. And you can see when radius decreases, it spins faster. Why? Because when the radius decreases, I, well, not I, capital I, inertia decreases, I don't decrease. But that means to compensate that decrease, it should spin faster. And we saw this device before. Now we can use it again. What's going to happen if I give it a spin? Oops. And let's say I'm going to pull on the string. The radius decreases, it spins faster. The radius increases, it spins slower. This actually happens at lots of places in the universe. When a neutron star ages, well, it spins, but in time, it loses mass, and it spins faster and faster and faster. And actually, they beam out radio waves, X-rays, and those beams can tell us how fast it spins. We can use this to measure age of this star or age of the universe. And the last experiment, standard, you can find lots of those experiments on YouTube. So again, I'm going to risk myself. You're in a fault zone. So what's going to happen if I'm, oops. If I turn it, because initially, when it was perpendicular to the vertical axis, the linear momentum was, angular momentum was 0. When this wheel has angular momentum, well, let's say clockwise, in order to compensate that, I have to start rotating in opposite direction. So you can try it if after the class, all these experiments. And let's just solve a specific problem, which related to an object dropped on a spinning disk, right? So initially we have a disk which spins, I don't know, counterclockwise, it doesn't really matter. And of course, we can calculate the angular momentum. Which is equal to the product of rotational inertia and initial angular velocity. And if that's a disk, yes? Yes. 1/2 mass radius squared times omega initial. All right. What's happening after the collision? That is a collision. That's why we can use again the law of conservation of that variable, angular momentum. Collision happens very quickly. So after the collision, we have disk with additional mass attached to it, spinning in the same direction, but as we will see soon, slower. We can predict it. We increase in inertia, so we should decrease angular speed. Final angular momentum of this system should include the initial inertia of a disk plus the inertia of that piece of clay. And that should be multiplied by the final angular velocity. And the law says in this collision, the total angular momentum should remain the same. So you can see by adding inertia, we're decreasing angular speed. The rest is math. Okay, so one more problem on the law of conservation of angular momentum. Well, I don't have a disk, but I have a device which can spin. And initially, it is at rest. And the bullet, this table is not leveled. Okay. The bullet flies and hits and gets caught in this catcher. So the question for you is, after that happens, what will be the direction of the motion of that disk or this device? Okay. Let's do it for the record. So frictionless, okay. So that's it. It starts spinning clockwise, and it is a collision. The law of conservation should work. We just have to apply it. However, the kind of tricky part is, actually I'm going to keep it for now. Tricky part is, it's a bullet which is flying straight ahead. So if you want to apply the law of conservation of linear momentum, this thing doesn't have it because it spins. If you want to apply the law of conservation of angular momentum, this doesn't rotate, just flies straight ahead. So what do we do? Well, first of all, we should understand the simple fact that if I shoot it here or here or here or here, it will not matter as long as I get the bullet inside, the effect will be exactly the same. The history doesn't matter. But if the history doesn't matter, this catcher doesn't know how the bullet was traveling before it hits it. For example, it could have been traveling, where's my circle? In a circle. Now someone stole my ball on a string. All right. This bullet could have been circulating with the same speed. The catcher doesn't know it. So when it hits, in that case, the angular momentum of this bullet would be the reason for this system to have a new angular momentum as a whole after the collision. That's the idea, which is physics. It's not about mathematics. So now we know what to do. We don't care about the history. We care about the bullet, which is hitting the disk right here. It travels at this speed. It has a given mass. But we could assume that it was not flying straight ahead, that it was rotating first before it hits the catcher. And if it was rotating, the angular speed of that rotation would have been equal to the linear speed of that bullet divided by the radius. And now we can calculate the effective angular momentum of this bullet before the collision, which is the initial angular momentum of a system because disk was at rest. And how do we do that? I times omega. A bullet is a tiny particle. The moment of inertia of that particle is mass times r squared. And we can replace the angular velocity with the linear over radius. That's it. That's our initial angular momentum. What about final? Well, after the collision, they spin together. So the final angular momentum will be equal to the rotational inertia of a disk plus rotational inertia of that bullet or mass times new angular velocity. And, well, that's the initial, that's the final. And according to the law of conservation of angular momentum, they have to be equal to each other. And that's it. All we have to do now is just finish the calculation. And don't forget, again, this is the diameter. Rolling. Rolling is a motion when an object simultaneously rotates and travels translationally. So it's a combination of rotational and translational motion, like every wheel does. That's rolling. That's rolling. When we look at the rolling object, we can look at the motion of a center of mass, and center of mass just travels straight ahead. And we can look at the motion of any point on the rim about the center of mass. And that's a rotational motion. And together, that's what we call rolling. Now, there are different types of rolling, complicated and simple. Complicated rolling happens when we can see some slipping. In that case, we can't say much about angular and linear variables. However, the simple case, rolling without slipping, tells us how to connect the linear variables which describe the motion of a center of mass and the angular variables which describe the motion about the center of mass. If you look at this simple experiment again, this yellow tape makes one whole revolution about the center of mass. So the distance traveled by this about the center of mass is equal to exactly one circumference. But if we look at the motion of this handle, it travels exactly the same distance. If they travel same distance, distance over time, same speed. So this type of a motion is very easy to analyze because rotational motion and linear motion are coupled, connected by this expression. The speed of the center of mass relative to the Earth is equal to the speed, the linear speed of the points spinning at the edge of this object, at the rim of this wheel, relative to the center of mass, relative to the axis, relative to the handle. So that's basically it. The rest is very, very straightforward. So we can always, in our mind, break any rotational motion into a combination of translational, or any rolling in a combination of translational and rotational motion. What do we know about translational motion? There's one word which answers that equation. Everything. What do we know about rotational motion? Everything. By transition, what do we know about rolling? Everything. So when an object rolls horizontally down a ramp, up the ramp, kinetic energy may remain constant or may change. And the easiest way to analyze what's happening is to apply work kinetic energy theorem. This equation in general has a term which might describe the force we are applying, like my hand pushes the handle. But in all our examples, we're only going to analyze a situation when an object rolls on its own and there is no slipping. So translational motion and rotational motion are always coupled together. Question. We have here 3 different objects which have different shape, but more or less same mass and more or less same size. A sphere, a hollow cylinder, and a solid cylinder. And we know how to calculate the moment of inertia for each. And the question is, how do you rank the moment of inertia of these 3 objects? Why is it important? Because after answering this question, you have to immediately answer another question. Immediately. If you know how to rank the inertia, you should use that information to answer the question, which object is going to win this race? If they roll down a ramp, when they released from rest from the same initial height. And what's good about physics, we can always test our predictions. So I'm going to release these three objects. I need a third hand. I'm going to let them go. You will see if your prediction was right or wrong. If it was wrong, everybody makes mistakes, so not a problem. If it was right, maybe you just guessed. Maybe you just got lucky. Did you enter your answers? What did you enter? How did you rank the inertias? Well, you answered the question number 7. Okay, but they're related, of course. But why did you choose that the sphere will win the race? Well, that's a good analogy. Yeah. It has less inertia, so it's going to be easier for the sphere in the same time to travel longer distance. So let's see. That's it. Question? Do you want to see it again? Do you want to see it again? All right. You say yes, I can show you again. You say no, I don't show you again. It's all for you. Works every time. Well, of course, the first question is just about numbers. We know that 1 is greater than a half, and a half is greater than 2/5. So we know that the sphere has the least inertial properties and less inertia, faster change of state. Well, I just want to do this math as an example of such calculation, but I want to do it once for all three objects simultaneously. Because as we know, for any object, the rotational inertia is equal to a certain number, a certain coefficient which has a name, a form factor times the mass times radius squared. And what we have here is an object rolling down the ramp. And the energy initial, mechanical energy initial will be equal to potential energy, which is mgh. Now, of course, each object has a certain size, but when we calculate potential energy, we neglect that size. Yeah. We just use the height of the ramp. And of course, the zero level is chosen at the bottom of the ramp. And there is no kinetic energy because it starts moving from rest. And the final energy will be equal to, well, now there is no potential energy, but because it's rolling, we should add kinetic energy due to translational motion of the center of mass and rotational kinetic energy due to rotational motion about the center of mass. And mgh should be equal to mv squared over 2 plus 1/2 times. Well, now we can use this expression for rotational inertia. Form factor times same mass times radius squared times. Now we have to use the fact that it's a rolling without slipping. So rotational motion and linear motion are coupled. So we can replace angular velocity with this ratio, linear velocity over radius squared, which makes our life much easier. Turns out we actually don't really need to know the radius, because in the last expression it will be cancelled. So what can we cancel? Mass, mass, mass. Radius squared. What's left? GH equals V squared over 2 plus 1/2 times form factor times V squared, which gives a simpler expression, because 1/2 V squared is a common factor, and we can keep in parentheses 1 plus form factor, which is 1 or 2/5 or 1/2. So what does it give us? That gives us final speed GH times 2 divided by 1 plus a form factor. Well, squared, and calculate the actual speed by taking the square root of this expression. Well, now we can use several possible reasonings to relate this speed with time. The easiest, from my point of view, is to make a statement that the average speed for all will be equal to actually mathematical average, because we know that from the past. It's a motion with constant acceleration for the center of mass. So initial plus final over 2, that's the average. On another hand, that should be equal to distance traveled over time. So time will be equal to 2 times distance traveled by the final speed. All right. Which leads us to 2 times distance, and we have to flip the fraction, so square root 1 plus c over square root of 2gh. And now we can see more inertia leads to more time. That's it. Less inertia, less time. This coefficient tells us what should happen to the time. We increase the form factor, it increases the time to travel the same distance. I've got slides which you can read. Same statement. And next question. Sphere won the race when 3 objects have been rolling down the ramp. What if I want to make a different race? In this problem, I roll a sphere down the ramp, and a piece of ice. Ice means no friction. So I have no ice, but instead I have almost frictionless cart. So I can roll them together. And the question is, which will win the race now? The fastest from the rolled objects, or an object which doesn't roll but slides down without friction? First of all, I want to mention the role of friction. We have had a discussion already that friction is not always bad. We wouldn't be able to walk or drive without friction. Now, let's say this is the absolutely frictionless, icy, oily surface. What would happen to the sphere if I let it go? It would just slide. It couldn't be spinned. Friction is needed to make it spin. So without friction at all, there wouldn't be any difference between a piece of ice or any sphere or cylinder. Friction makes that difference because it also wants to make it spin. And that should provide some extra inertia. And the rule is always the same. More inertial, more time. Less inertia, less time. So now the cart is less inertial, and that's why it wins. If the cart also would have been spinning, that would require extra inertia. And, well, who knows what would happen? We would have to actually calculate different inertias. And mathematically, of course, we know what to do. Mathematically, the expression for the sphere is still the same as we have derived before. Time for the sphere is equal to, what was it? 2 times s square root of 1 plus c over square root of gh. Let's test my short memory. Another 2. Yes. So the question, what do you think should I write as a form factor for the sphere? 2/5. The equation for the cart should be the same. But what should I write as a form factor for the cart if it doesn't roll at all? If it doesn't roll at all, no rotation, no means what? 0, nothing. You have solved this problem before. So that's why the time to reach the bottom of the ramp for the cart is less than the time to reach the bottom of the ramp for the sphere. That's why the cart wins the race now. Well, a couple of more examples. A ball rolls. Oops. How does it roll? Horizontally. Okay. So probably the question about the ramp will go to tomorrow, and probably tomorrow we will have some extra time for your questions if you have them, or for the new material if you have no questions. All right, so a ball. We didn't have any equation with the name ball. We had an equations with the names like cylinder, sphere, disk. So what should I write for the moment of inertia or for the form factor for this object? Sphere, we know ball is a spherical object. The moment of inertia 2/5. Mass radius squared, or the form factor is 2/5. And the center of mass of this object travels at 2 meters per second relative to the ground. So we know that we could calculate the kinetic energy, which should be equal to 1/2 mv squared. V represents the velocity of the center of mass relative to the ground, plus 1/2 I omega squared. And from the first look, it looks like we may missing some important information. We know the mass, okay. We know the speed. And that immediately gives the kinetic energy for translational motion. But we don't know I. And if we try to calculate it, we don't know the radius. And every time when that situation happens, we give up. I can do it. Or we believe that it's solvable, and we proceed, and we enact the actions in exactly the same way as we would act if we knew everything we think we would have to know. So we continue our calculations. 10 plus r squared times. And now we can employ the fact that in this motion, angular and linear variables are coupled, related. So the angular velocity should be equal to linear over radius squared, which leads again to elimination of the unknown. So as long as we believe, you just have to keep walking. Now the question is about the work which should be done. Well, if the object has to be stopped, so final kinetic energy should be equal to 0. That means the amount of work which should be done should be equal to the magnitude of the change of kinetic energy, which is 14 joules. Okay, we can do that. So now the same ramp, and a cylinder starts from rest, rolls down the ramp, inclined at 30 degrees. And it travels 4 meters. So please go to the website and prepare to answer the next question. I don't know the number, what it was. So the question is, four meters is measured here. Answer number 2, 4 meters is measured here. And the answer number 3, 4 meters is measured here. The answer number 4, there is no ramp. Answer number 5, I don't like physics. The answer number 6, for people who are watching I'm not here. I'm just giving you time to choose your answer. All right. What question is it? 7? 8. 8. Thank you. Scroll down. Okay. In this case, physics and democracy agree. Distance traveled as measured for the distance traveled by the center of mass should be equal to the magnitude of the displacement of the center of mass, and the center of mass travels parallel to the surface of the ramp. So 4 represents the hypotenuse of this ramp. But if 4 is hypotenuse, so the height, which we're going to use, the height will be equal to hypotenuse times sine of 30, which is 2 meters. Now we can start writing the equations, and the equations are, well, the initial kinetic energy will be equal to 0, but the initial potential energy, gravitational potential energy, will be equal to 2 times 10 times 2 relative to the ground. So naturally, the 0 level for potential energy is chosen at the lowest location, which is at the bottom of the ramp, the joules. So the mechanical energy initial is equal to 40 joules. Now, at the bottom, final potential energy is 0. We chose that level to be equal to 0. But final kinetic energy should include 2 terms: translational kinetic energy for the motion as a whole, plus rotational kinetic energy for the rotational motion about the center of mass. And the law of conservation of mechanical energy tells us 40 joules should be equal to 1/2 times 2 times speed, which we need to calculate, plus 1/2 times, that's a disk, so form factor equals 1/2 times mass times unknown radius squared, but now we're not scared, because we know it should be equal to that same final speed divided by the same radius squared. And again, we can see that the radius getting canceled. The only unknown left in that equation is that final speed we are looking for, and you can solve that unknown by doing simple algebra. Any questions? Because I still have time for one more problem. All right. Now, of course, we roll it up the ramp. It's the same ramp. So the distance traveled is the same. And now we are looking for the speed, the initial speed of the center of mass. And it should travel 4 meters up and should stop here, so the final speed will be equal to 0. But we know that means the height will be 2 meters above the ground, above the bottom of the ramp. So because the angle is 30 degrees. Well, we know what to do. Because the approach to the problem cannot depend on the direction of the motion of an object. It's still about energy. Now, initial mechanical energy will be equal to initial potential energy plus initial kinetic energy, which is equal to 0 plus 1/2 mv squared initial plus 1/2 I omega initial squared. And now mechanical energy final will be equal to mgh plus 0 kinetic energy. It stops there. And if we apply the law of conservation of mechanical energy, that tells us that 1/2 times 2 times the unknown squared plus 1/2 times, that's a cylinder, so the form factor equals 1/2 times mass times radius squared times searching for clues without slipping means angular and linear velocities are coupled. Same initial speed, but over the radius squared. Initial, I said initial. And again, the only unknown left in this expression equals to 2 times 10 times 2, actually same number. So the only unknown left is that initial speed. Before we go, what would be different if this ramp would have been completely frictionless? No friction. No friction means what? As we have discussed it. No rotation. No rotation means the kinetic energy now has only one term, 1/2 mv squared. Well, technically, we could have write plus 1/2 I omega squared, but now omega is not equal v over r because there is no coupling. Now omega equals 0 because there is no rotation. All right, thank you. I'll see you tomorrow, and have a nice day. Don't forget, we have a lab, right? Oh, no, we don't have a lab. No, we don't have a lab. Don't forget, we don't have a lab. Don't go to the lab. No, we do have a lab. Don't forget we have a lab. Go to the lab. Yes, we don't have it on Monday. Hi. Yes.
Just so I can get in time and like be able to use it. It's in 138.
136, 138 doesn't exist.
Well, that's what your slide says. Or 136.
136.